Okay, thank you very much. So I must say, first of all, that I'm presenting the work on behalf of the first author of this presentation, which is Elisa Casella, postdoc at University of Genoa. So I'm responsible just in part and blame her for everything wrong on this. Huh? So I will try to bring you in a classic site for coastal studies in Italy, which is Liguria region in the northwestern Mediterranean Sea, where actually we have a situation where we have more or less every 10 years a coastal monitoring study provided by the regional authority. Most of these studies are related to aerial photographs from where they extract the shorelines after the ortho-rectification. So we have a series of shorelines, the last one in 2003, and then we have coming up a LiDAR done by the Italian Ministry of Environment in 2013. Unfortunately, the data are not yet available, but they will be soon, we hope. And then we have superimposed to this ordinary monitoring, exceptional monitoring that are done more or less once every year in case there are some construction works, for example, this submerged island, and for coastal defense and restoration. So every year, basically, there are monitoring works that are related to bathymetry, more or less, coastline evolution, etc. So this is just the evolution of these studies in 2013, up to 2013 from 2009. And this is a very common situation along, I would say, most Mediterranean coastlines, but also most European coastlines. We just do the monitoring when we need it. But for science, most of the times we have actually to do monitoring when it's more interesting. We want to get short-term changes maybe along coastal areas. We want to be able to monitor what happens after a major storm in some coastal areas. So I think you know where I'm going due to the title of this session. We started to wonder if it's possible to get orthophotos when actually we want them and more accurate topography when we actually need it. So we started experimenting about 4 years ago with small unmanned aerial vehicles. For the Italian laws now, they are called remotely piloted aircraft systems, whatever that means. And basically, we started experimenting with a microcopter, Octo XL, which is a octocopter basically, and the typical result you will get after you apply the photogrammetric techniques and the structure from motion techniques that have been described so well before is basically something like this. You obtain an ortho-rectified picture of the shoreline, and if you place ground control points and you measure them with accurate GPS, you can also create a DEM of the shoreline. Now, I would like to draw your attention towards the accuracy that we can obtain, the vertical accuracy especially that we can obtain in such a flat environment. Now here I did an experiment to see what was the worst case scenario. So I took ground control points, these green dots, that were really at the border of my area, so where less pictures were overlapping, so where the destruction from motion is actually bad, worse than in maybe central areas here. And what we get is something around plus or minus 20 centimeters, which is not perfect, but I'm confident that we are doing GPS surveys in these areas, and we are starting to see the vertical errors decrease down to plus or minus 10 centimeters, which is quite fine, I would say. After we started to experiment with these kind of drones, we wanted a little bit more. We started to say, well, sometimes we need something that is more easily usable and cheaper, and maybe can be employed also in developing countries. So in some places where we can actually teach people to use it and send us the data that we can, and then we can build on that, build knowledge on that. So we started to experiment also with a DJI Phantom. And again, the results of the vertical accuracy, it's about pretty much the same. This is a flight we did after a major storm that happened in Italy, 25th of December 2013. And basically, we got a pretty good, with 90 pictures. We were flying the DJI Phantom without GPS, just flying over the study area because it was a serendipity moment because the microcopter was broken. We realized we broke the barometric sensor as soon as we lifted it. So to do the job done, we used this, and it actually worked. Another thing we usually look when we are in coastal areas is when everybody works in coastal area wants to know if my measurement matches where the water is. So, well, this is the result of the photogrammetry. This is the 3D, the digital elevation model obtained from structure from motion. And this is the land-water boundary. It's quite well represented, so we were confident. And then I'm spend the next few minutes to basically go over one or two examples that I obtained at Zoom in this area. So the first result was when we started to do comparative studies. So we went to the same area and we started to do multiple flights. So this is an example of every point you see here. The green dots are ground control points that we use to georeference our image and 3D models, while the small black dots are control points, and you have also small red dots that are static control points where we have GPS accuracy of plus or minus 2-3 centimeters vertical. Again, if you take something that is really at the border of your picture, of your overlapping, you get accuracy plus or minus 20 centimeters. So I'm going to go with this. I know probably in these places is much better, but I'm going to go with plus or minus 20 centimeters. So we can start to use the digital elevation models. We can actually start to play with them and subtract them. So subtract the different flights one each other, and this is a temporal evolution. So I subtracted the first flight done in November from the second flight done in December, and then the flight in December minus the one in March, and we can start to look at changes along this coastal area. Of course, we also have an idea of during our surveys what happened. So this is what you're looking at is a wave height graph. This gray band represents the wave data registered at a buoy, which is offshore, and then we used hydrodynamic models to represent the onshore conditions. So the black line is the onshore condition. This area you can see here is sheltered. So actually, most of the times you see reduced wave height at your site. But it's very interesting. At some point we started, this is still in progress, but we started to think about this. And it's very interesting to see that while in the first moment, we have quite calm condition and mostly small waves coming from this way, they're probably enough to cause some sediment shift from here to there. Where you see some blue here, there is some teeny tiny blue here, means that you have an accumulation of sediments, and you have a small coastal retreat there. And then you have here another coastal retreat, and here you have a big blue bar, and this big blue bar is just human activities. They were basically quarrying sand from here and bringing sand up there. This big red, for example, this big red part there is basically due to the fact that they cut the trees, and in one part of this study area there were a few trees and they just cut them. What is more interesting is that we can start to see how the beach behaves once the big storms, big for the Mediterranean of course, but some of them are fairly big, 3-4 meters, significant wave height on shore, starts to react. And it's actually quite interesting to see that most of it, except this part, which is probably caused by few pictures overlapping, so we don't have a lot of accuracy here. But a lot of this is, we see coastal advancing, and we see also an aggradation of the shoreline, probably by 30-40 centimeters of aggradation of the shoreline. So we are looking at something that we couldn't see if we weren't using these techniques. And also while we were experimenting with drones always on these coastal areas, we saw, first of all, modal value storms hitting our shorelines. And we saw even, I already showed you these bigger storms hitting the shorelines. To give you an idea, we have a storm like this probably twice every year. This one is probably one every 10 years. It has a 10 years return time. So what we did was actually start to combine what we obtained with the drones with what is our bread, which is coastal dynamics. And we used multi-beam data merged with the topography we obtained with drones, and we applied the modeling chain basically to calculate the run-up of waves coming along these transects to see where the run-up would be. And we started to make some comparison between observed run-up, so this will be the wet line, so where the waves are coming up, and modeled run-up. And actually, this is very interesting because this is the first time that you can do this with relatively little effort. It took us probably 20 minutes to get the data for this. Otherwise, it would have taken us probably few hours to get the data walking on the beach with a GPS trying to find the wet line. And this is the first time we are really thinking about the fact that we can do we can survey multiple storms in multiple areas and actually compare observed and modeled run-up to tune our models. So these models were done mostly for oceanic areas. DHY has been done mostly for North Sea areas. So we can start to have a look at processes comparing with observations. So I entitled the lessons learned. We learned a few lessons. The first one is that UAVs are wonderful for coastal management. Actually, we are thinking about, we are writing projects in different, to work with them in different countries. As I said, also in developing countries, they might be, oh, I'm running out of time. There might be actually a very nice added value. We're working in Ghana, where, for example, they have meters of coastal erosion every storm that comes. So it would be very nice to actually have a picture of this, a detailed picture of this. So they fill a gap in time and space between surveys. We have fair enough precision, fair enough accuracy. If you wanna, we know what we know what we wanna do, and they will probably likely be the tool for coastal management in the future. And as a lot of people ask me about drones, when I speak about this, my answer is usually, well, you have to know what you want. First of all, if you have small areas, small budget, difficult accessibility, easy to use, we have seen that before. It's not a sin to use a DJI Phantom, which is basically born to be a toy for this kind of science. And larger areas, better cameras and positioning are required. Well, it's possible to use UAVs up to 3-8 kilos, or even fixed wings. We are experimenting with that. But then don't complain about regulations that are starting to be tighter and tighter across Europe, and I know also in the US. So I'll leave it at that. Thank you very much.